Next I'm going to introduce the concept of efficiency, and then we're going to try to measure the efficiency of 3 different ways to heat up water. On a stove, yeah, and we have a pot. Now the heat from the combustion, which we can call Q combustion, doesn't only go inside the pot. But what goes inside the pot? Some goes inside the pot, some goes outside of the pot. So this is going to be called Q waste, and it's going to be called Q useful, which is the one that we computed before. So what we want to know is how much QC we need to produce the QU that we want. We always have to take into account that there's going to be a waste. So we can define in this situation the efficiency of this process, which is going to be called eta, and it's going to be the useful energy that we need divided by what we spend, which is the energy from the fuel. So how much fuel we're putting into this action. Now if your fuel is natural gas, you can easily understand this by knowing how much volume of natural gas you have spent and how much is the energy per unit of volume of natural gas that you can release by combustion. If you use an electric stove, you can just measure the electrical current going in, and if you know the voltage, you're gonna know the power, and so if you know also the time, you can calculate the amount of electrical energy that's been spent to do the same action. For this video, the idea is to show how we can easily have a rough estimation of how much is this efficiency and compare the efficiency with some different methods. Now, as I said, we want to measure how much is the efficiency of this process for 3 different methods. First method is going to be high flame and pot without lid. So there's going to be evaporation losses and losses in the air of the flame itself. Then the second method is going to be small stove with same pot but with a lid. And the last method is with just an electric kettle, and which has electric power coming in. Now for these 2, it's very easy to measure the amount of gas that I'm burning because I can read it from the gas counter that's just behind my kitchen. For the electric kettle, it's a little different because I cannot just turn off everything that's in the house to measure these on the counter. So the best thing I can do is just read the power of this device and just count the time that it takes to boil the water, so that I can from P, read P, and I multiply by time, and I'll get the energy. Let's do the efficient way to boil water on the stoves. You can see the temperature of the water. It's now from the tap at 17.6 degrees. Let's pour this water inside the pot. So here's the place where we can read the gas, the amount of gas that's been burned. So now I'm gonna light the fire on a low flame and start the timer at the same time, so that we can know how much gas we consume, how much time we use. 3, 2, 1. Okay, so time is going, the fire is burning. As you can see, I'm using a small stove, so the speed is very limited. Now, as you can see, on a small stove like this, you cannot see the flame coming outside from the sides of the pot. This is good because compared to the method with the bigger stove, you don't lose as much energy on the sides. This means that the gases, when they arrive here, I can actually put my hand here without burning myself. It's still hot, so it's still going to be some air that goes up and loses it to the external environment and doesn't go inside the pot. So the efficiency will not be 100%, of course, and it's going to be much higher than compared to a bigger stove. We're going to have to see if the time is much longer or not. And of course, by using the lid, you avoid big part of the evaporation. Another thing I want to say is the positions of the pot on the stove is very important as well. So we have to make sure that the stove is right in the middle of the bottom of the pot. Okay, so now it's probably boiling. I see a lot of vapor coming out, and yes, it's boiling, and I'd say completely. So let's stop the time, and the stove. So this is the final value for the gas. I'm going to make the difference to understand how much energy we actually use, and this is the final time. One last thing we want to measure is the temperature of these pipes which bring the gas to the stoves, so that we can adjust the density of the gas, because of course to know the energy for each volume of gas we need to know the density of the gas. And so let's measure it. 17.8 degrees here and 18.2 here. So the problem is the pipe is not at the temperature that the gas is, but it's something in between the outside temperature and the gas temperature. But yes, I'll make a little adjustment. It's still gonna be some error, but yes, we have 1 liter of water at tap temperature, which is around 17.5 degrees. We're gonna boil it in the same pot that we used last time with a more efficient method. But this time we're gonna use no lid and a big stove. With the amount of gas we are burning, and I'll turn it on. Where are the energy losses here? We have 3 main energy losses. The main one will be the flame being almost as large as the pot. A lot of heat is gonna radiate outside from the sides, and also it's gonna fly away with in the form of hot air and just not go into the pot, which is where we want it to go. Second loss is evaporation. Now that the temperature is still low, it's not very important, but when the temperature rises around 70, 80, 90 degrees, when it's still not boiling but it's almost there, yeah, then it's gonna be a huge loss. So the third loss can be considered a loss by conduction, which can happen on the sides. Some of the heat will go from the water to the metal and from the metal to the air, but it's a very small loss, in my opinion, compared to the loss from the flame and from the evaporation. Okay, now let's try with the electric kettle. You can read the information about this. The only thing I'm going to measure now is the time that it takes for the boiler to boil the water, and I'm going to assume that the energy is just the time multiplied by an average power, which would be the power which this thing has at 230 volts. Turn the power on and the time at the same time, and go. You cannot really read it. Now, what are the losses of this system, since we're talking about efficiency? So basically this just converts electrical power into heat in the resistor that's inside here. So it's quite efficient because all the electric power is now nowhere to go but inside the metal, and the metal is submerged by water. So all the heat released in the metal will eventually go into the water. The problem is you still have some losses, because of course when there's water at 90 degrees inside and you touch here, you can still feel it's not very hot, but you still can feel it's around 40 degrees, 50 degrees. So some heat is going to be lost through this surface to the external air. And also there will be some evaporation here, not that much, because there's a... Okay, now it's boiling. I stopped the time. So it was in total 3 minutes 19 seconds to boil this water. With this value we can compute the energy. So we just measured the amount of energy we need to increase the temperature of water from the temperature of the tap to 100 degrees Celsius, so to its boiling point, with 3 different methods. So let's make a table. So here we put kettle, here we put pot, inefficient, and here we left pot, efficient. Now we measure time for energy, and we will give the value of efficiency. So time, we have the values, we measure the values, so we can write them without doing any further calculation. And the units are seconds. Now what about the energy? Let's start talking about the kettle. So the kettle had a rated power that goes between these two values, and the voltage is rated to be between 220 volts and 240 volts. Now in Portugal, where I live now, the voltage is 230 volts. We're going to use this value, and for this value our power will be, so the energy spent in this first method is energy equals power times time, which gives us 3.78 times 10 to the 5th joules. So let's put it here, and the units will be joules. And we can also compute the efficiency at this point by dividing the value of the energy we need by this value. The useful energy is so we call it QU, is 3.48 times 10 to the 5th joule. I know we got a slightly different value before, which was 3.55 times 10 to the 5th, but that was because we assumed that water temperature of 15 degrees out of the tap. Actually, I measured it, and the water out of the tap is around 17, 18 degrees. So this is for 17 degrees Celsius. And so the efficiency for this value was around 92%, which is these divided by these, with a non-efficient pot. Now the energy here must be extrapolated from the values of volume of gas consumed that we read. And we have a delta V, which is what V here mean volume. Let's call it VO, so VO, so it's different from voltage. For the inefficient method, we have a difference of around 33 liters. So how do we move from liters of gas to energy of gas? We need information about the heating value of the gas. So first you need to know actually what kind of gas you have, because we're talking about natural gas, but natural gas varies slightly from country to country depending on where it comes from and where it was extracted, and if something was added to it. I found that for the gas that I'm using in my house, the values should be around, inferior heating value should be around 38. I mean, this is the value that I found that shouldn't be much different from what it is in reality. So this is megajoules on normal cubic meter. Normal cubic meter means a cubic meter measured at 0 degrees Celsius and 1 atmosphere of pressure. Now we need to adjust this value because these are not the conditions in which our gas is. In fact, the temperature is around, let's say the temperature is it's also around 17 degrees Celsius, but let's use a easier value, which is, let's assume that the temperature is T of the gas equals 20 degrees Celsius. So we have to take into account the fact that at 20 degrees Celsius there are fewer molecules in 1 cubic meter compared to at 0 degrees Celsius. This means that our, so let's call this normal IHV, and let's call the one we're going to use IHV, which is equals to IHV normal times T normal divided by T, which is this one, so let's call it T gas. And this must go in Kelvin because it's not a subtraction is a ratio, and this is 273, and this will be 293. So we are adjusting the value to take into account the fact that we are not in normal conditions. And this gives us, regarding the pressure, we can assume that the pressure is actually pretty close to atmospheric pressure, so we don't need any further adjustment. This is because the gas inside the pipes cannot be at lower pressure than their atmospheric pressure. Otherwise, when we open the gas, there will be air flowing inside the pipes instead of gas flowing from the pipes to the air, and this is not possible. And also it will be slightly higher than atmospheric pressure, but not that much higher, because it would be dangerous to have high pressure gas inside the pipes. So we can assume that it's almost equal to atmospheric pressure. So with this value, now energy, what is the energy that we have? Energy must equal the amount of volume, so let's call it delta, this one, times the energy per each cubic meter of volume, so it's H GHG, inferior caloric value. Now here I'm using inferior caloric value, or heating value. It's not actually correct because inferior heating value is used when there is no condensation. Actually here we have some condensation. As soon as you light the fire and there is cold water in the pot, you can see condensation on the sides of the pot. But then actually the same water that condenses on the sides of the pot is then again evaporated, and probably that evaporation is mostly due to the same heat that is from the pot. So during the boiling process we will have some moments when we're using a superior heating value and some moments where we're using an inferior heating value. I'm using the inferior heating value here because in the end you end up with no water, with no condensation, so I assume that you're not actually using that energy. I mean, you use it in the beginning and then you lose it in the end, so it's good to use this one. So this goes 33 times 10 to the minus 3 because we want cubic meter, not liters, times 35.79, which is the value we obtain here. And here we have a 10 to the 6th because it's megajoule, in the end with 1 joules. And so we end up with a value of 11.8 times 10 to joules. An efficiency of just 3, we can do 3.48 divided by 11.8. This value divided by this value, and this equals 29.5%, so just around 30%. Okay, let's move to the last situation, in which we have efficient pot, in which we have a delta volume of 22 liters. So energy would be using the same approximation as we did before, 7.87 times 10 to the 5th joules. So the efficiency will be around 44%. Okay, now that we have a complete table, we can make some comparisons. So we can see from only this point of view, which is the final energy to useful energy transformation, the most efficient way to boil water is the kettle. Yeah, the second is the efficient way to cook with the pot, and the third is the inefficient pot. These are just examples. These values could change a lot if you just have a little bit of water, and maybe I didn't measure very well the liter of water, so could be there are for sure many errors in these values. Just to give you an idea of what's the difference between various appliances. I'm not going to say that efficiency of cooking in a pot with a lid is 44%. It's not a fixed value. It can change depending on many factors like how big the pot is, how many water is in the pot, how high is the flame. But this is just to give you an idea that probably the kettle is the most efficient way. And we're not considering also that it actually takes almost 1/3 of the time of the second most efficient method.